Okay, I'm going to try and teach the muscles lesson today that I had planned remotely with the help of my able assistant, who's currently holding the camera as we've broken the tripod. So we're going to take you through the lesson as I had it planned. So starting with a starter activity, okay, based on what we learned last lesson. So can you have a read through with me now and then pause the video while you answer, and then I will show you the answer as well. Okay, so what you can see is a longitudinal section through the myofibril, which you'll remember from last lesson is the bundle of protein fibres, of which there are two types: thin actin myofilaments and thick myosin myofilaments. Okay, so the question first of all asks you to calculate the length of band X. Okay, so for that you will need the length of X as an image size in millimeters, which is 95 millimeters. Okay, so you can use that to calculate the length, the real length of band X. And then you need to explain the difference in the transverse sections A and C. Okay, so if you pause there and give it a go, we're going to go through the answers now. Okay, so we need to have a look at the paper. Super. So we've got 95 millimeters as the image size. Okay, we want our answer in micrometers, so I always convert straight away into micrometers by timesing by 1,000. So it's 95,000 micrometers is the image size. Remember from last year, it's image divided by magnification to give us the real or object size. So my magnification was 40,000, so I just take that divided by 40,000, and the answer is 2.375 or 2.4 micrometers. Okay, and then for the other part, if you go back to the screen, Charlotte, you're just looking at you've got C has myosin, the thick fibres, and actin, the thin fibres or filaments. So the fact you've got both present overlapping in C. This is an old spec question, so I think you'd require all of that on the new spec. A contains only actin, or these are the thin myofilaments, I think would be required on the new spec. Right, let's get cracking on the next bit then. So in your keynotes, you need to turn now to this section. So we did our myofibrils, we did the contractile, the arrangement, relaxed versus contractile last lesson. We did all the shading and the banding patterns. So now we're moving on to how, when a nerve impulse stimulates a muscle cell, so when that acetylcholine diffuses across the synapse and binds to receptors on the muscle cell membrane, the sarcolemma membrane, how does this increased overlap between the actin and the myosin happen? So that's what this section is about and what the rest of the video is going to be about today. Okay, and it's called sliding filament theory. So you need to be using this section of your notes, which is at the bottom of page 6, alongside what I talk about. Okay, so I'm going to show you a picture with the arrangement that's described here. Okay, so there is the thin filament, which is the actin, okay, which is this bit here. That is actually wrapped, when you look at it much more closely, by a second protein called tropomyosin. Okay, the thick filament, the myosin, we'll see that's got a lot of heads that stick up on its surface, and when the myofibril is relaxed, the tropomyosin is actually like a rope, and it's wrapped around the actin and it covers the filament up, so the myosin, these heads, can't attach. So let me show you a picture of that first of all in our relaxed muscle, I'm going to use, oh, it keeps doing that, it keeps changing animation on me. Okay, so here, before we start, you can see a relaxed arrangement. So the white rope-like protein, that is tropomyosin. The purple is the thin actin, so you can see it here sort of represented in this animation. And the tropomyosin is wrapped tightly around the actin, so it's covering all the binding sites. So even though the myosin heads are there, they can't bind to anything at that time. Okay, so back into your keynotes. So what happens? Well, the first thing to note is that it's all about calcium ions being released. So when the action potential, the depolarization arrives at the sarcomere, it spreads through the T tubules and calcium ions diffuse into the myofilaments from the sarcoplasmic reticulum. So they're released from the sarcoplasmic reticulum and they diffuse into the myofibrils. So that's where we've got this arrangement of actin and myosin myofilaments. The calcium ions then affect the tropomyosin on the actin. Okay, so let me show you that bit in the animation. So the green dots, they are the calcium 2+. You can see when they join, the tropomyosin moves, changes shape because it's a protein, and reveals these binding sites on the actin structure for the myosin heads. Now you can see on the animation the name of another molecule that's completely off spec. So troponin is not something you need to know about for AQA. So for those people who do want to know, it's when the calcium 2+ binds to the troponin that is associated with the tropomyosin and it causes that change. But for us, as in our notes, calcium 2+ just causes the tropomyosin to move off the actin myosin binding sites. So now you can see that the myosin heads can bind to their binding sites, and that's what they do. Okay, now already you can see in this animation that ATP's been used earlier, it's been hydrolyzed earlier before this step. Now it is a cycle and we're kind of joining at this point. So there's some energy stored in this head already. And that energy is used for the head, once it binds, to nod, we say. So it makes a nod or a power stroke, sometimes talked about. Now in this animation you'll see the phosphate and the ADP are lost during that process. That's not important at A level. What's important is the energy that was already in the head has allowed it to change shape and move. And as it's done that, you can see all these heads, they are, if I make it bigger as well, you see them here in this animation. If I go back and we watch them, okay, as they do that, they're going to be moving this actin so that both sets are working and moving the actin closer together. Okay, so back into our keynotes. Okay, so we said this movement causes the exposure of the myosin binding sites on the actin. The myosin head attaches to the binding sites. You can say forming a cross bridge. That's usually what I say, or an actin myosin bridge. But actually on our spec, I would highlight cross bridge as being the most important key term. Okay. So at A level, we can kind of talk about the energy that's the result of the hydrolysis of ATP is what was stored in the head and causes the head to nod forward. So we'd seen that that had already happened in that particular animation. For us, as long as we get it in somewhere, that's important. We do need to know that it's hydrolyzed, it's been broken down into ADP and phosphates. And then we saw in the animation the nodding of the myosin head pulling the actin towards the myosin. Okay, so back into our animation for the next bit. Okay, so the nodding's happened. We can see that because of the position. Now comes in a new ATP molecule. And that is a really important step because you require the ATP for the cross bridge to break. If we didn't have any ATP, that would not happen. Okay, and if that happens, then the whole cycle starts again. So the ATP is hydrolyzed within the head. The energy is stored in the head. The head returns to its original position, and a new cross bridge can form with the next binding site along. And then the head will nod again, and this will continue and continue and continue as long as there is ATP available for this to happen. Okay, so if we go back into our keynote, well, we've got that summarised. So the attachment to the new ATP molecule to each myosin head causes the myosin head to detach from the actin sites and separate it from the actin, returning it to its original shape. This process repeats, moving the actin along a bit more each time. So well, that's not a bit cool. Okay, so we've got those sort of set events to kind of categorise in your head, and that's a kind of a 5-mark description. Okay, there is an AO2 on this, and if you move to the next page, you'll see if the stimulation of the nerves, if the nerve keeps releasing acetylcholine and acetylcholine keeps binding to receptors on the sarcoplasmic membrane, so that on the sarcomere, on the muscle cell membrane, sodium will continue to move in, and it will continue to cause calcium ions to move from the sarcoplasmic reticulum to the myofibril, and this will continue to happen. But if it stops, then the cell pumps the calcium back into the sarcoplasmic reticulum, and the tropomyosin returns to its original position, and the muscle fibre relaxes, so all the filaments slide back into their original position. Okay, I think that I've said that all right. I did start with the if there is no stimulation. So if there is stimulation, calcium ions will still be released and you'll still get this effect. If stimulation stops, they won't be released, they'll be pumped back in. Tropomyosin will return to its original position because there's no calcium 2+ bound anymore, and the muscle fibre relaxes. Okay. Right, so I want us to go now into the student notes, into the question pack. So look at question 1, okay? So if we could zoom in on question 1, is that okay? I'll let you have a go at question 1, okay? And I'll finish this video here and start our next video on the answer to that question. So could you have a go at question 1, which continues part C on the next page? Thank you.